Hello, this is Unit 8, Day 1 for Algebra 2, Polynomial Functions. And today we're mostly going to be talking about end behavior. So example 1 is a throwback from Algebra 1. Write the following polynomials in standard form. Determine the degree of the polynomial. That's what we need for our lesson in Algebra 2. So remember to put polynomials in order. You put the highest exponent first, and then in decreasing order for exponents. The degree of that polynomial is the degree of the highest monomial term, which is 4. So basically your highest exponent if you only have x's. Next one, x plus 3 is in order, and this is a first degree polynomial because the exponent on the x is 1. H of x would be x to the 5th plus 10x squared minus 3x plus 5. The degree of that polynomial is the 5 because that's the highest exponent. And the last one is only one term, and it's in order. And since there are no variables, the degree of this last one is 0. Alright, so we're going to talk about graphs of polynomial functions. You've dealt a lot with quadratic graphs and parabolas. You have seen cubic graphs and have talked about those, but not really anything past that. So the fundamental theorem of algebra states that an nth degree, so whatever, fill in whatever you need for n, so 5th degree, 8th degree, 9th degree, an nth degree polynomial will have at most n real roots. So if you have a 5th degree polynomial, it will have at most 5 real roots. And what they mean by real roots is crossing the x-axis. Okay, so if your graph crosses the x-axis, that is a real numbered root. So for example, a 3rd degree polynomial can cross the axis at most 3 times. Doesn't mean it will cross 3 times, just that it can and it will never go over. Likewise, an nth degree polynomial will have at most n minus 1 turning points. For example, a 4th degree polynomial, so that means the n is 4, can have at most 3 turning points. So the number of turning points that it can have at a maximum is 1 less than the degree of the polynomial. Alright, so on the left we have a graph of a cubic function because the degree is 3. And if you look, it hits the x-axis 3 times, so it has 3 real roots. And it has a turning point here that's called a relative minimum, and a turning point here which is called a relative maximum. The reason why they call it relative is because technically this graph will go to positive infinity forever and negative infinity forever, so there is no max or min for real. But in this general area where infinity is not involved, that's the highest point that I've labeled in red, and this is the lowest point down here. So it's a relative max and min. On the next one, you have a degree of 4, so 4th degree polynomial. Remember, it will hit the x-axis at most 4 times. Well, this one only hits twice. So what that means is you have 2 real roots because it hits the x-axis. And back in Algebra 1, we used to tell you that whatever your highest exponent is how many answers, which are the roots, you're going to get. So if this graph is only showing 2 real roots, that means you also have 2 imaginary roots because you need to have 4 roots total. Okay? And then, according to the theorem, it will have at most 3 turning points. Here's a turning point, and here's a turning point, and then that little hook there in the middle may or may not be one. Wouldn't be able to tell without further investigation, but remember, it said no more than 3 turning points, so we can easily see 2 of them. Alright, so an nth degree polynomial may have exactly n complex roots. A complex number, remember, is a plus bi, so it's got a real and an imaginary part. So essentially those are the imaginary roots. For example, it is possible for a fourth degree polynomial to have either 0, 2, or 4 roots over the complex number system. So think imaginary roots here. Imaginary. Okay. Note, imaginary roots will not appear as x-intercepts. You are not going to see imaginary roots on a graph. Okay, just like when we had a quadratic. What are the roots? Doesn't have any. But if you solve that quadratic equation, you will get two imaginary roots. Okay, same thing here. Now, you get those imaginary roots by using the quadratic formula. And the quadratic formula has b plus or minus blah blah blah, b squared minus 4ac all over 2a. But the piece I want to highlight here is the plus or minus. So when you get done solving, you have two answers, one with a plus and one with a minus. So the point is that all complex and imaginary roots come in conjugate pairs. That means if you have one imaginary answer, you got to have another one, guaranteed, because they come in conjugate pairs. Remember, conjugate is where one's a plus and one's a minus, and that's the only difference. Okay, so you got to remember those always come in pairs. Okay, same thing happens with irrational roots. Irrationals are the ones where the square root doesn't go away, which comes from the quadratic formula. You will also get conjugate pairs. All right, so that's why you can only have an even number of imaginary roots or irrational roots. All right, before we dive too far into that, we're going to talk about the end behavior of the polynomials. So what we mean by the end behavior is as x goes toward infinity, what happens to the graph? As x goes toward negative infinity, what happens to the graph? So this is very similar to domain and range. In fact, it is domain and range, it's just asked in a different form. So if you have an even degreed polynomial that has a positive leading coefficient, so in other words, if you have y equals ax to the fourth, plus whatever, doesn't matter. Okay, so your leading coefficient's the one that touches the highest degree x value. All right, if this exponent is even, I don't care if it's 2, 4, 6, 8, 10, 212, okay, then the end behavior of that polynomial will always be the same. All right, so what's going to happen for the end behavior? This notation, which you're going to see a lot of in pre-calculus, says as x approaches negative infinity. So that arrow means approaches. So as x approaches negative infinity, well, that's this direction, right? So x is a horizontal movement, left for negative infinity. So as your graph approaches negative infinity, they want to know what your graph is going to do if you have an even degree with a positive leading coefficient. Well, it's going to go up to positive infinity. And then on the right it says as x approaches positive infinity, so that means as x travels toward the right, they want to know what happens to f of x, and f of x is a y. So see how we're really doing just domain and range. So as the domain approaches positive infinity, that means it goes all the way to the right. They want to know what happens to the y value. Well, it also approaches infinity. So what they're really saying here is that every graph that has an even exponent and a positive leading coefficient is going to end with the tails pointing up. Well, positive is up and even means they match. What happens in between those two ends is going to vary a great deal, but the two ends themselves will look like what I've drawn. All right, so I want to go to the one underneath it first. If you have an even degree again with a negative leading coefficient. Now on the example above, the even degree, they both the tails of my graph ended up pointing up to the positives. Well, if it has an even degree, my tails will go in the same direction. So if I have a negative leading coefficient, hopefully you've guessed by now that that means that both tails, both ends of my graph are going to be pointing down toward negative infinity. So this notation says as x approaches negative infinity, so as you're looking toward the left of the graph, my f of x, my y, is also going to approach negative infinity. As x approaches positive infinity, which means as you're looking toward the right, what's going to happen to the y value? Well, it's going to go to negative infinity as well. So when you have an even degree, the tails match. They either both go up or they both go down, depending on whether you have a positive or negative. So let's go over to the odds. If you have an odd degree and a positive leading coefficient, your tails are going to go into opposite directions. So if the leading coefficient is positive, it's going to go up to the right, which are both positive directions, down to the left, which are both negative directions. Excuse me. As x approaches negative infinity, as x goes to the left, your y value is approaching negative infinity because it's going down. As x approaches positive infinity, that means it's going toward the right, then your y value is going to positive infinity because it's going up. Okay, so for odd, up and to the right, both positive, down to the left, both negative, and two negatives make a positive. The odd degree, so if you have an odd exponent with a negative leading coefficient, switches those. So instead of up to the right, it's going down to the right and up to the left. So as x approaches negative infinity, as it goes toward the left, our graph is going to go up to positive infinity, and if you look, one of them is negative. Well, one negative makes a negative if you think about multiply. So negative leading coefficient. As x approaches infinity, that means as you look to the right, your y value is going toward negative infinity. Okay? And you're going to want to know those four outcomes for your tails. Alright, so this got cut off, but we'll deal with it. Draw a rough sketch of a third degree polynomial with 3 real roots and a positive leading coefficient. Alright, so third degree polynomial means it's going to turn twice. 3 real roots means it's going to hit the x-axis 3 times. And a positive leading coefficient. So when the degree is odd, my tails are opposite. So when it's a positive coefficient, it's up to the right and down to the left, because up and right are both positive, down left are both negatives, which turns into a positive. Okay, so here we go. You can place it anywhere on the grid. You just have to hit the axis 3 times, turn twice, have an ending that goes up to the right and down to the left. So here's my up to the right. So I gotta hit x-axis, turn, hit it again, turn, hit it again, and go down to the left. It's a cubic function. Okay, so I've hit 3 times, turned twice, and my tails are in the right position. Okay. Number 2. 4th degree polynomial with only 2 real roots and a negative leading coefficient. Alright, so 4th degree means I'm going to turn at most 3 times. 2 real roots means it hits the x-axis twice. Okay. Negative leading coefficient. Alright, 4th degree is even. That means my tails match. They either both go up or both go down. And negative leading coefficient means they both go down. Alright, so I need a tail that goes down. I'm going to turn at most 3 times. I have to hit the x-axis twice. So hit once, turn, oh, can't hit it yet, turn, oh, turn again, and down we go. So there's my 3 turns. hits the x-axis twice, and my tails are both pointing down. Alright, third degree polynomial with only one real root and a positive leading coefficient. Alright, it's odd, so the tails are opposite. O for odd, O for opposite. Positive leading coefficient means I'm going to go up right and down left. I'm going to turn twice. One real root. Well, if there's a third degree polynomial, I have 3 roots total. Only one of them is real, which means I'm only going to hit the x-axis once. Alright, so my left tail has to look like this. I'm going to go ahead and hit the x-axis. That's the only time I'm allowed to do that, but I got to turn twice. So there's 1 turn, 2 turns, and I just make sure I turn again before I hit the x-axis. So here's my 1 root, my 2 turns, and my tails are opposite. Okay. Draw a rough sketch of a 4th degree polynomial with a double real root, positive end behavior. So 4th degree is even, that means my tails match. Positive means they're going to both go up. A double real root. So what a double root is when you have the same root twice. So you get the same number twice for a root. So that happens in special circumstances in quadratics when we're factoring, but essentially to get a double root, that means your vertex is the root. So one of your turns has to be on the x-axis. Now, because it's 4th degree, that's 3 turns, but if I only have 2 real roots because it's a double, then one of the turns does not hit the x-axis. Alright, so left-hand side has to look like this. We said the vertex has to be the root. So I'm going to come down here and make my vertex be my x-axis, or hit the x-axis. That's a double root. Now, my end behavior has to be up in the air, and I want to turn 3 times. So there's turn number 2, turn number 3, and back up in the air I go. So this, where the vertex turns, is a double root. Number 5, draw a rough sketch of a 5th degree polynomial. No imaginary roots. That means they're all real, and we have to have 5 roots. Okay, 5 real roots. And a negative leading coefficient. So if it's odd, the tails are opposite. So negative leading coefficient means it's going to go backwards. So I'm going to go down to the right and up to the left. Alright, so here's up to the left. I need to hit the x-axis 5 times. 1, 2, 3, 4, 5, and down we go. Alright, now you could have squished all the roots onto the negative side. You could have squished them all onto the positive side. You could mix them up like I did. There is some flexibility in how you draw these as far as where you put your roots. But the end behaviors have to be the same. The amount of turns and the amount of roots. Where those are located, that's a little bit flexible. Number 6, draw a rough sketch of a cubic function. So that's 3rd degree, so odd, with a double root and a negative leading coefficient. So the tails are opposite. So negative leading coefficient, so it's down and to the right and up and to the left. A double root means it's a double real root. They have not specified about any other roots. Well, that gives me 2. I've only got 1 left. That 1 root cannot be imaginary because imaginary roots always come in pairs. So if they want a cubic function with a double root, they're going to be getting another real root. Otherwise, this problem's impossible. Okay? So this is the only part they cared about. Your 3rd root has to be real. You cannot have it imaginary. Alright, so here's my tail. Double root I can do now or later. I'll do it later just for grins and giggles. So there's my one extra root. Turn once, turn on the x-axis, and go down. So here's my double root. Okay. Now I could have gone like this, where I'd come down. Here's my double root. Whoa, what's that doing? Come down, there's my double root. Come up and then cross. That's also another way to draw it. So in an even degree polynomial graph, the tails will match. If the A is positive, the tails will both go up. If it's negative, they'll both go down. A can't be 0 because then you get rid of your first term and you don't have that kind of graph anymore. If it's an odd degree polynomial graph, the tails will be opposite. If the A is greater than 0, the left tail goes down, the right tail goes up. If it's negative, the left tail goes up and the right tail goes down. Alright, so real quick before the homework. Without graphing, identify the end behavior of the polynomial function. So the degree of the first one is 5. Sign of the LC, that stands for leading coefficient. Leading coefficient is positive. So that means we're going to be going up to the right and down to the left. As x approaches negative infinity is on the left, so the y value goes down to negative infinity. As x approaches positive infinity, that means it's going to the right. Our y value is going to positive infinity because it's going up. Alright, number 2, the degree is 1. The sign of the leading coefficient is negative. So that means the tails will be opposite, and it's going to be down to the right and up to the left. So as x goes to negative infinity on the left, y is going up to positive infinity. As x goes to positive infinity on the right, y is going to negative infinity. Alright, number 3, the degree is 4. The leading coefficient is positive. That means my tails match because it's even and they go up. So as x approaches negative infinity, the y goes to positive infinity both times. They're both going up. Alright, number 4 is not in standard form. They give you space to write it. We don't need to do that. The degree is 3, which makes 5 the leading coefficient, so it's positive. So they're opposites, up to the right, down to the left. So as x goes to negative infinity, which is the left, we're going down. And as x goes to the right to positive infinity, we're going up. Alright, number 5. Ooh, this one's a tricky one. Let's go ahead and write it in standard form. If I combine like terms, my x to the 6 goes away, so I'm left with negative 4x squared plus 1, making my degree 2, and my leading coefficient negative. Because it's an even degree, my tails match. Because it's negative, they both go down. So both of these go to negative infinity without even having to think about it. Alright, this one, the degree is 6. The sign of your leading coefficient is negative. That means the tails match. They go down both times. Alright, you will have similar problems for your homework. Good luck.